Hello, this is Math Jazz from Almost Cool, and today is another math live stream. Today we're going to talk about maximization and optimization using matrices rather than using derivatives. So there are a few constraints that are required for our problems here, and we will discuss those now. So this method, which is called linear programming, this method only works when you have linear constraints and a linear objective function. Okay, so z is to be maximized. These are our requirements. And z is linear in our xi's. 2, all of our xi's are greater than or equal to 0. And 3, all of our constraints are of the form a1 x1 plus a2 x2 plus up to a n x n are less than or equal to b, which is greater than or equal to 0. So these are our requirements. We need to have a linear z. We're maximizing it. All of our independent variables have to be greater than or equal to 0, and we have to be able to write all of our constraints as a linear combination of our variables, our independent variables, less than some constraint which is greater than or equal to 0. Okay, so those are our requirements. And what I mean by a linear function is, of course, that all of the powers are first powers, and all of our terms have exactly one variable, and so basically z is of this form. Z is equal to some constant times our first variable plus some constant times our second variable up to some constant times our last variable. So we're trying to maximize a z that is in this form. Okay, so knowing that these are our constraints, here is our method. Okay, first we have to set up the matrix. Okay, this matrix will be constructed as follows. Remember all of our constraint functions. Well, we will have the first constraint function, which I will have a11 as the constant related to the x1 variable. So the first one represents first equation, the second one represents the coefficient on the first variable. So we're going to set up a matrix that looks like this. We're going to introduce something called a slack variable. We're going to introduce one slack variable for every constraint function. And then over here, we'll go this is our constant, and it'll be b1 because this is the constant associated with the first equation. So if we have this constraint a11 x1, a12 x2, a13 x3, all the way up to 1n xn is less than b1, that becomes a row like this. A11, A12, up to A1n, 1 for the first equation. We get a 1 under the first slack variable. Zeros for all the other slack variables. And then our constant b1 goes here. Okay, so the next row would be, of course, using the second equation. You take the coefficient of the first variable for the second equation, the coefficient of the second variable in the second equation, up to the coefficient on the last variable in the second equation, so 2n, second equation, last variable. You get a 0 here because this is the second equation, not the first. You get a 1 here because this is the second slack variable and the second equation. You get zeros in all the other slack variables, and then you have your constant for your second equation. You go all the way down until your last constraint. A n1, A n2, sorry, m1, there are m equations, and n variables. There we go. m1, m2. Here's our last equation's last coefficient. So the m row nth column. We get zeros in all of our slack variables except the last one, because this is the last equation, so it goes with our last slack variable. And, oh, I forgot. We have to have a z column, which will have zeros all except for the bottom row. But we can fit that in. Okay, so now we have our m constant here, and a 0 for z. And now what we do is we look at our function to be maximized, which is this z equals c1x1 plus c2x2 up to cnxn. These go in negatively, so negative c1, negative c2, up to negative cn, 0 in all of the slack variables, 1 for the z, and a 0 over here. Well, because we didn't have a constant. But if we had a constant, we'd put it here. And it would be positive. Okay, so we have this, and now we have this matrix, and we have to do our simplex procedure on it. Now I'm going to do the simplex procedure on a specific matrix rather than this general one here. So that means we're going to have to come up with a specific example. Okay, so let us get a specific linear programming function to maximize, and we will go from there. So here we go. We have z is equal to x1 minus x2 plus 2x3 and then now that we have this, we need our constraints. Of course, one of the constraints is that all of our variables are positive, so of course xi is greater than or equal to 0. And then our other constraints, well, let's have that x1 plus x2 plus 10 x3 is less than, let's pick 100. And let's turn the camera so that it's straight. There we go. We have x, let's have 5x1 minus x2 plus 2x3 is less than or equal to, let's say, 150. And that's probably good for us there. Okay, so here's our what's it called? The objective function. There we go. Objective function, and here are our constraints. We're trying to maximize z. So let's set up our matrix. I'll leave these here. So here's our x1 row of our matrix. I'm going to put a 1 here. Here's our x2 row of our matrix. We'll put a 1 here. And here, x3 of our matrix, we will put a 1 here. We have two equations, so we'll have two slack variables. So here's our first slack variable and our second slack variable. Since this is the first equation, we'll put 1 under the first slack variable and 0 under the second. Here's our z column. There are no z's in this constraint, so we'll put a 0. And then our constant is 100. And then we close off our matrix. Okay, so this is what we have for our first row of our matrix. Okay, first row of our matrix. Second row, we get the same way. We're going to have 5x1 minus 1x2 plus 2x3. This is the second equation, so it gets a 1 in the second slack variable. It has no z's in it, and its constant was 150. There we go. And the last row, since we've used both of our non-trivial, I'm going to call these the trivial constraints, because they're required to do this procedure. The non-trivial constraints, we have 2 of them, and we have 2 rows representing the 2 of them. So now our last row is always going to be the z row. Okay, and we take these coefficients, which are 1, -1, and 2, and we flip them negative, so we get -1, 1, and -2. There are no slack variables in our optimize. There are no slack variables for our objective function, but there is a z, so we put a 1 in the z column. And then our constant is 0. Great. So now we have this as our matrix. Okay, so going back to our general matrix for a moment. These entries here in this rectangle, so all but this one at the end, that one doesn't count. This entry at the very end of the row doesn't count. All of the other bottom entries are called indicators. So the first step is we need to figure out which indicator is the most negative indicator. That is the one with the largest absolute value and is negative. So over here, looking at this, -2 is our most negative indicator because 1 is not negative and -1 is not quite as big a number as -2. The other numbers are not negative, so they don't count. So this is called our indicator. I'm going to put a nice little box around that. Sorry, this is our most negative indicator. They're all indicators, but that's the most negative one. Now from here, that indicates that this row is called the pivot column. Sorry, this column is called the pivot column. So we have our indicator, our most negative indicator, and our pivot column. Okay, so from here, we take our pivot column and we have to find our pivot entry. So the way that we do that is we look at the constant column, and we divide by the corresponding element in the pivot column. So 100 divided by 1 is called our pivot ratio, or one of our pivot ratios. (100/1) is equal to 100. Our other pivot ratio is the constant column entry, which is 150, divided by our pivot column entry in the same row, 150/2. Which is equal to 75. Once we find all of our pivot ratios, we look at the one that is smallest but positive. So this is 0 divided by -2, which is 0. 0 is not positive, so it does not count. Throw that out. 75, therefore, is our pivot ratio, or the smallest positive pivot ratio. And that means that since this is the row that gave us the smallest possible pivot ratio, the second row, this is our pivot row. And the place where the pivot row and the pivot column intersect is called the pivot. This is the pivot row, this is the pivot column, 2 is the pivot. Now, what we have to do now is we need to figure out how to use row operations to eliminate all elements in the pivot column that are not the pivot. So the pivot is 2. That means 1 and -2 are not the pivot. We need to get rid of both of them using legal row operations. Okay, so doing that does not change our middle row. So I copy the middle row exactly as it is, -1, 2, 0, 1, 0, 150. Now I want to get the first row. So looking at the first row, the way to get rid of this 1 is to take 2 times the top row away from the middle row. So 2 minus 2 times 1 is 0. And I'm going to have to do that in all of my columns for this computation. So I'll start here. 5 minus 2 times 1 is 3. -1 minus 2 times 1 is -3. 2 minus 2 times 1 is 0. 0 minus 2 times 1 is -2. I'm going to stop moving this. 1 minus 2 times 0 is 1. 0 minus 2 times 0 is 0. 150 minus 2 times 100 is 150 minus 200, which is -50. And I've copied them across on my top row of my matrix. Now I do the same thing for this third row. So I figure the way to get rid of this is to take the second row and the third row and add them together, because 2 minus 2 is 0. So we get 5 minus 1 is 4. 5 minus 1 is 4. -1 plus 1 is 0. 2 minus 2 is 0. 0 minus 0 is 0. 1 minus 0 is 1. 1 plus 1 is 1. And 150 plus 0 is 150. Now I look at my new matrix after that procedure. I now no longer have a negative, which means that I am now done with the process. And so what this matrix tells me, the way to read this, since I say that this has the answer to how to maximize our z value given the constraints that we had, is you look at all of the columns that have only one non-zero entry. This has a 2 and 2 zeros. This has a -2 and 2 zeros. And this has a 1 and 2 zeros. And I look around, those are the only ones that have exactly one non-zero entry. The other ones do not, so I'm going to put a cross above these. And now I recall that this was my x1 row. Because this row has more than one non-zero entry, the value of this variable that will maximize my z is 0. This is my x2 row. It also has more than one non-zero entry, so the value that maximizes it is also 0. This is my x3 column. This is one that I boxed because it has exactly one non-zero entry. And what I do is I take this non-zero entry, go across to the constant, and do the ratio of the constant over the non-zero entry. So 150 divided by 2. So 150 divided by 2 is the value of x3, since this is the x3 column, that will maximize my z value. This is my S1 column. So -50 over -2 will maximize my S2 column. Sorry, S1 column. So that's going to be 25. And then we have, this is our S2 column. And it's going to be 0. And then this is our Z column. The last one is our Z column. 150 over 1 is going to be 150. So what this tells me is that the point 0, 0, 75 is the place where my Z is maximized, and its value is 150. So this is my answer to my maximization problem. Okay, so I did this procedure without proof, but let us write up at least a flowchart for this procedure. Okay, so the first thing to know about this procedure, the first step is find most negative indicator. If all positive, or if all non-negative, done. If not, go to step 2. Step 2 is find least or smallest, find the smallest positive pivot ratio. That determines the pivot row. The first determines the pivot column, the second determines the pivot row. Okay? Third, eliminate pivot column except for pivot. And when you're done with that, return to step 1. Okay, so the first step, find the most negative indicator. If none, you're done with your matrix and you get to read off your entries. 2, find the smallest positive pivot ratio. If there's no positive pivot ratio, then you have no solution, which is different from being done. Having all non-negative indicators means that you are done, you have an answer. Having a non-positive, having no positive ratios means that you're done, there's no solution. Oh, and in both cases, if you have a tie for most negative indicator, use the one on the left, or the one furthest to the left if you have multiple entries in your tie. You have 3 or 4 that are all most negative together and tied. Take the one furthest to the left. The smallest positive pivot ratio. If there's a tie for smallest positive pivot ratio, use the one that's furthest up, closest to the top. Okay? And then after those things, you've found your pivot row and column, eliminate all but the pivot in the column, and then return to step 1. When you get to the point that all of your indicators are positive, or I guess if none of your pivot ratios are positive, you're done, and you figure out what your matrix tells you. The way that you read your matrices are, if you have all zeros except one entry, so like this is called a non-basic variable. It means that this value here is the denominator on your fraction that tells you the value of the variable, and this is the numerator. So you let 100 be the numerator, 1 be the denominator. That tells you the value for s. On rows that have no non-zero, on rows that have more than one non-zero entry, you let those variables be 0. And so that's how we read our matrices, just like we did here. We read off our matrix. When we got all of our indicators were positive, that indicates that we're done. We read off the 3 columns that have exactly one non-zero entry in them to get the values for those variables. And we killed off the variables that had more than one non-zero entry, setting them equal to 0. So I hope you enjoyed this episode. We will talk about how to use this procedure to minimize a function on Thursday. So see you then. Hope you have a great time learning mathematics, and if you have any questions, please email them to mathjazz9@gmail.com. That is now on the screen, mathjazz9@gmail.com. And again, thank you for watching. Have a great day. See you Thursday. Bye.